What we're going to look at next is finding parameterizations of certain types of surfaces. Not all surfaces are easy to come up with a parameterization for, even if we can do it. We're going to just look at a few kind of simple examples of scenarios where we can do it fairly without too much trouble. The first example is thinking about a situation where the surface is a function. So let's say, for instance, that could look like z equals f of xy. You could also have one of the other variables be a function of the other two. A simple parameterization is, if we think about kind of comparing this back to when we did parameterized curves, well, we said let the independent variable be the parameter, and then just let the dependent variable depend on that independent variable. So in this case, my independent variables would be both x and y. So we can have, say, x of uv is, let's just say, a single parameter u, y of uv is the other parameter v, and so then z of uv just becomes f of, instead of xy, it's just uv. So plugging in those other two variables there. So then we get r of uv would just be like ui plus vj plus f of uvk. So basically our two parameters in the x and y components, and then just use the actual function in the y and the z component. Or you could change those up depending on which are your independent variables and which is your dependent variable. So like a specific example is if we have the upper half cone, z equals the square root of x squared plus y squared, then we could just say let r of uv equals, say, u I plus v j plus the square root of u squared plus v squared k. And what we can see is that's going to give the same points that the curve up above would give. So it's just essentially, in that case, then a different way of storing that function information. Now, we would have the ability then to kind of adjust this if we wanted, if we wanted a different, if we wanted the cone to be parameterized using different portions of u and v, so not necessarily starting at something like 0 and continuing on. We could do that. The next thing I want to look at, though, is a slightly more interesting case besides just simply looking at functions, is to look at surfaces of revolution. So these were that idea where you take a curve, so let's say revolve the graph of maybe y equals f of x about the x-axis. So that might look something like down here, we'd have like a y equals f of x function is going to live, say, like in the xy plane, and then we're going to take that and we're going to revolve it around the x-axis. So then what we're going to get is we're going to get this kind of coming up and creating a nice like circular portion up here. We'd have it coming around the back, and this would have a circular part around here. So what we can see, these are types of surfaces, we looked at them back in like Calc 2, for instance, so their cross sections are all circular. So what we could do then is we could say, let the axis we're revolving around is, say, in this case, the x-axis, so we could let x be u. And then what we could do for y and z is we could represent them by kind of a circular cross-section. So like if we look right down the x-axis at this, what we're going to see is the zy plane, or the yz plane, I suppose. And all of its cross-sections are going to be circular, where what we're going to see is the radius of those circles is going to be defined by whatever this function that we had was. So this is like that f of x function. So that's what this distance is going to end up being. So then what we can see is to represent all of these points on that cross section of the circle is we could kind of think about it similar to polar coordinates. So we've got like our horizontal axis, we could do, say, the f function times a cosine of an angle, which we'll just use v as our other parameter. And then on the inside of f would be x, but we've let x be u. So it'd be like f of u times cosine v, and then z could be f of u times sine of v, would give us those points there. If we had switched the sine and the cosine, it would just trace it in a different way. Similar to parametric curves, these parametric surfaces are not unique. So we can have multiple ways of representing the same surface. But just to kind of show you an example of what this could look like, is say, like, for example, revolve 1 over x about the x-axis for x from 1 to 10. So we could just simply let x be u, be a parameter, and then we could let y be the function, which in this case would be 1 over u, and then times cosine of another parameter, say v, and then z be 1 over u times sine of that other parameter, say v. So then we would have something like r of uv would be ui plus 1 over u cosine v plus 1 over u sine, 1 over u cosine v times j, I missed my j, plus 1 over u sine v times k, and then if we put bounds on these, well, u is the same as x, so u is going to range from 1 to 10, and then v, since they are sine and cosine, we could just do a single period of those functions, which would be 0 to 2 pi, would give one full rotation. So that could be our parametrization for that curve. It would look similar to this one that I drew up above, where this would keep getting asymptotically closer and closer to the x-axis. It's actually a famous historical surface called Gabriel's horn, and has some really interesting properties to it. So one of the things that we'll notice is, right, we rotated about a particular axis in that one. We can make adjustments for that. So if we change the axis, then we can just kind of do the same process but changing accordingly. So like, for example, say we instead rotate x equals f of z about the z-axis. Well, now what we would see is we would have in our r of uv, z would be kind of my independent first parameter. So we would have u times k. So z would be u. And then this time what we're doing is we're rotating about that z-axis. So all of my cross sections are going to end up circular about the z-axis. So then they're going to be circles relative to x and y. So we could have like f of u, say cosine v for x, which would be our I component, and then we could have like f of u sine of v times our y component, which would be j, and then that would be plus the u of k. If you want to use something like a theta instead of a v, go for it. It totally doesn't matter. You could even just use z instead of u. It doesn't matter what you name your variables. It just matters how we put them into our parameterization.